Hello, this is Dr. Maxwell, and our next topic is our first application of the derivative. So we've learned all the derivative rules, and now we are going to use the derivative mostly to analyze graphs. But this is an application that's also important, and those of you who are planning on taking physics, you will see this, I'm pretty sure. Um, it's the relationship between the position of an object, its velocity, and acceleration. It's very interesting. And the derivative can be used to analyze motion along a line or vertical um, motion of an object. So we usually let S of t be the function that gives the position of an object at time t. T can be in seconds or hours or minutes, etc. So we have to pay attention to that. And then it turns out, and we'll look at this in a little more detail, that velocity is the derivative of the position function. And we'll see why this is so. And speed is the absolute value of velocity. So velocity has a sign associated with it. When it's positive, it's moving one direction, maybe to the right. And then when it's negative, it would be moving to the left. Depends on the setup of the problem, but it's opposite directions, negative and positive. And acceleration, in turn, is the derivative of the velocity and the second derivative of the position function. So why is this so? Let's look at an example. Here is a function that gives the position of an object in meters at time t in seconds. So if we look at the secant line, what does this represent? Well, this is the change in the y values, but in this case, it's the change in position over the change in time. So this would be the average velocity over that time interval. The change in position over the change in time. Think of that. It's meters per second. So if this is the slope of the secant line, it gives us the average rate of change, which would be the average speed. Then the derivative is the instantaneous rate of change. So that's the velocity at time t. So this allows us to find the velocity at a particular time t just by finding the derivative of the position function. So here is the relationship, meters per second, and that is how we measure velocity. Now, for acceleration, well, this represents the change in velocity. If your velocity is constant, you don't feel any acceleration, but when the velocity changes, you feel it. So acceleration could be looked at as the instantaneous rate of change of velocity. So we have this relationship. You have the position function. The derivative of the position function is the instantaneous change in position with respect to time. That's velocity. The second derivative is going to be the derivative of the velocity, which is the instantaneous change in velocity, which is acceleration. So it's quite an interesting thing. So we will have some vocabulary to learn, and we will look at this first example. This function gives the position of some object, and when time t equals 0, this object is down here. It's 14 meters to your left. You can imagine that you are standing right here at the origin looking at this object. At time t equals 0, it's 14 meters to your left, and it's traveling towards you. It's traveling to the right. And then it gets up here at approximately 1.5. The object is a little bit to your right, and then it turns around and it goes back to the left at time approximately 5 seconds. The object is down here, some 25 meters to your left, or 24 meters, I forget exactly, and it turns around again and then starts traveling to the right. So that's how we can interpret the motion of the object from the graph. And let's look at these questions over here. The total displacement is the net change in distance, net change in position, rather. So you take, if we want to find the total displacement from time t equals 0 to time t equals 7, we find s of t7. So what is s of 7 minus s of 0? Well, s of 7 happens to be 0. S of 0 is negative 14. So this is 14 meters. So the total displacement in this time period from 0 to 7 seconds, that's here to here, the total displacement is 14 meters. Now, find the average velocity over the same time interval. Well, this is the change in position, which we already know is 14 meters, over the change in time, which is simply 7 seconds. So the average velocity in that time interval is what? 2 meters per second. And next, we're going to use the graph to estimate at what time the body changes directions. Okay, let's get a new page. Okay, so when does it change directions? That's when it's going to the left, and then right here where we have this horizontal tangent, the object changes direction. So think about what that means. That means when s prime of t equals 0, or when the velocity equals 0. That's a possible time when the object changes direction. We can see that it actually happens because we have the graph. So this happens at approximately 1.5 seconds. You might say, why don't I know exactly? Well, I do, but it's What does the velocity function look like? Let's find it. It would be the derivative of this function. So velocity is 3t squared minus 20t plus 23. And you have to use the quadratic formula to solve this equation. And that's what I did, and then I just approximated the irrational number right here. And then we also have a change in direction down here when t equals approximately 5 seconds. So I did solve this equation with the quadratic formula for getting the zeros, and then just approximated my answer. But we're just asked to use the graph. And we've already talked about D, but we can say it in a little more detail. When is the object traveling to the left? Well, that's when, let's do right first because we start off going to the right. We're going to the right in these time intervals from 0 to 1.5 seconds and from 5 to 8 seconds, say, because that's where our graph sort of ends. And I'll show you that here too. So this is when I'm traveling to the right in these intervals, and then I'm traveling to the left in the other ones from 1.5 to 5 seconds, traveling to the left. Okay, so we'll look at another very classic example. We can also model an object's motion when it travels vertically, either when something is thrown up in the air or something is dropped. And we have this thing called gravity on our planet that makes things fall down when you throw them up. And G, gravity, is the acceleration. So how is acceleration related to velocity? We said something about this already. Acceleration is the rate of change of velocity. So here is how acceleration fits into this formulas. It's the second derivative of the position function. It's the first derivative of the velocity function. So this is a classic example. Dynamite has launched some rock up into the air with an initial velocity of 160 feet per second. And its position function is given by this equation. T is in feet, S of t is in feet, and t is in seconds. So our first question is, how high does the rock go? Well, you have to think about this for a minute. It goes up and then it comes back down, right? So what happens at this maximum height? What happens there? The velocity is 0 for an instant. And more than that happens, it changes sign. What does it change from? It changes from positive to negative there. So let's see what the velocity function looks like. Remember, it's the derivative of this function. So velocity is negative 32t plus 160. We set that equal to 0 and solve for t. Well, let's see what we get. We would get 160 equals 32t, and that tells me that t equals 5 seconds. So that is, and we can check, does the velocity actually change signs there? So how would I do that? I just make a number line. Here's 5 seconds. We don't want to go beyond 0 because we start at time t equals 0. And I'm going to check the sign of the velocity function on either side of t equals 5. So I can plug in something here. Maybe I'll just plug in 1. So when you plug in 1 to the velocity function, is it positive or negative? It's positive, right? And on the other side, I could plug in 6. And I'll have to check that. If we actually do this one, you plug in 6, you would get negative 192 plus 160. And yes, that's negative. So that confirms that we changed direction. We were going up and then we were going down. So that answers this, does not answer the question, does it? We just know when it happens now. So how high does it go? How do we find that? The maximum height happens at t equals 5 seconds. What is the height? For that, we need to plug it into the position function. Okay, so let's find the position at t equals 5. We're not doing this. Scratch that out for now. What is the position? 5 squared is 25. So do this calculation, and we will see that at t equals 5 seconds, the position is 400 feet. So that is the answer to the first question. How high does it go? So what did we have to do? We had to figure out when it reached the maximum height, and we found that was t equals 5 seconds. And then to find the actual height, you have to go back to the position function and plug in t equals 5. Now we'll tackle this part B. So don't look at this part. We'll just do this. What are the velocity and the speed when it is 256 feet above the ground? So we already know that it goes up 400 feet and then it starts falling, right? So at some point, it does reach 256 feet, right? So we want to find the velocity at that point and the speed. So what do we need to do? We need to find out when is the rock 256 feet above ground. So we need to find the time again. So how are we going to do that? Well, this is a height, so we use the position function. So in other words, when does this equal 256? So take this function and set it equal to 256. All right. This is a quadratic, so I need to get 0 on one side and hope that I can factor it. And what I'm going to do is factor out this negative 16 and see how this looks. That gives me t squared plus, nope, not plus, minus 10t plus whatever 256 divided by 16 is. I think that's 16. And then I make sure I did my signs right. Because see, I factored out a negative 16, so I should change these signs, and that looks good to me. So this does factor. T minus 8, t minus 2. So the time, the when, this happens at two different times, at t equal 2 seconds and t equal 8 seconds. So does that make sense? Yes, because it does it on the way up and it does it on the way down. So now we have our times. We just need to find the velocity and the speed. So let's get a new page. Okay, so our velocity function, remember, is negative 32t plus 160. So we plug in 2 seconds, and we will plug in 8 seconds, and evaluate the function. So for when time equals 2, the velocity is 96 meters per second. It's positive, so it's going up. And at 8 seconds, it's 96 meters per second. It's negative, though, so it's going down. Now that's velocity. Speed is the absolute value of velocity. It doesn't have a sign. So the speed is just 90. Oh, and this is feet, my bad. Feet per second. So this is 92 feet per second is the speed. So how did we do this? Well, this time we had to find the position, use the position function to find out when it was 256 feet above the ground. Once we got the time, then we plugged it into the velocity function to find the velocity and the speed. Two more questions to answer. What is the acceleration of the rock at any time t during its flight? Okay, let's see what we're talking about. The velocity, which is the first derivative, acceleration is the derivative of the velocity function. So this is just negative 32. What are we talking about? Well, it's negative 32 feet per second squared. And what is this? This is acceleration due to gravity. And that's the approximate acceleration due to gravity, the constant g. And the last question, when does the rock hit the ground? Okay, well, what is S of t when the rock hits the ground? 0 feet, right? When you hit the ground, you're at 0 feet. So we need to take this and set it equal to 0. And again, this is quadratic, so I'm going to factor, first thing I'm going to do though, well, I'm going to factor out negative 16t. That's what I'm going to do. And that will give me t minus 10 in here. So S of t equals 0 when t equals 0 and when t equals 10. So why do we have 2? Well, this is when it took off, and this is when it landed. So the answer to this is 10 seconds later. So it went up, and 10 seconds later, it hit the ground. Okay, what we're going to do is look at the graph and just see if we can make sense of this. This is the position function. And you see there's the maximum height. It went up to 400 meters. What do you think this is? Well, notice that it's 0 when we're at the maximum height. It's positive from time t equals 0 all the way up to t equals 5. And then it's negative down here from 5 to 10 seconds. So this is the velocity function. Let me erase that so you can see it better. This just represented 256 feet. And to show you that it happens twice. On the way up, remember it happened at 2 seconds. And then on the way down, it happened at 8 seconds. So this graph is just kind of interesting to see all these relationships. In particular, the derivative and the original function. I didn't graph acceleration, but what was it? It was a constant function, negative 32. So it would be somewhere like this, acceleration like that, negative 32. Okay, so we have some practice problems to work, and we will take a little break here and then come back, do a recap, and then do some practice.